we learn a little of Laplace transform. Laplace transform and Fourier transform are very important part in, it has got a lot of applications. So we'll study little bit of Laplace transform. It was introduced by Simon Marquis, a French mathematician. The word transform itself indicates a conversion of one form to the other. Laplace transform is a versatile tool for solving differential equation as it converts a differential equation to algebraic equation. Algebraic equations are very easy to solve. So once this ODE is converted to the algebraic form, it is very easy to find the solution for that. Laplace transform is used for analog circuit design, in control theory, signaling process, robotics. It has got wide applications. Now, what is the Laplace transform? Let f of t be a real valued function where t is defined between 0 to infinity, and the Laplace transform of this real valued function f of t is defined as 0 to infinity, integral 0 to infinity, e raised to minus st ft dt, provided the integral exists, where s is a parameter. And you know that L of f of t gets converted to f of s. So we are moving from t to s. T is a time domain and s is a frequency domain. So Laplace transform actually pushes the real valued function to the frequency domain. Now, basic properties of Laplace transform. The main properties of Laplace transform, which we widely use, is linearity property and first shifting property. So linearity property says that when you take the Laplace transform of two real valued functions, f of t and g of t, which is in turn having coefficients c1 and c2, the c1 and c2 are not affected by the Laplace transform. Can bring it out. So L of C1 into Ft plus or minus C2 into G of t will be C1 into L of f of t plus C2 into L of G of t. C1 and C2 are constants in differentiation also. Constants can be taken out and then we can differentiate the inner function. So same thing happens here. Laplace transform, constants are not affected by the Laplace transform. Now we come to the first shifting property. If L of f of t is equal to f of s, f of t is a real valued function. When you take Laplace transform of the real valued function, you get it to the frequency domain. So it gets converted to f of s. Now, L of e raised to at into f of t. E raised to at is an exponential function which is multiplied to the real valued function. So when you take Laplace transform of the exponential function with the real valued function f of t, then we get f of s minus a. Your s, the frequency domain, gets shifted to s minus a. So that exponential function multiplied with our f of t really brings in a change in the frequency domain. F of s becomes f of s minus a. Now, what are the applications of the shift property? We learned the Laplace transform of t raised to n, cosine function, hyperbolic function. Okay, so Laplace transform of t raised to n is n factorial by s raised to n plus 1. But when e raised to at comes along with t raised to n, then the Laplace transform of the present function gets shifted to n factorial by s minus a the whole raised to n plus 1. The change is coming for the frequency function. It gets shifted to s minus a. Again, L of cos bt. L of cos bt will be s by s square plus b square. But when e raised to at comes with the cos bt, the s gets shifted to s minus a. So the Laplace transform of e raised to at into cos bt is s minus a by s minus a the whole square plus b square. Again, when it comes to the sine function, we have L of sine bt as b by s square plus b square. Wherever S comes, we can observe that the shifting property happens. S get converted to S minus A. Again, for the hyperbolic function, unlike the trigonometric function, L of cos h bt will be S by S square minus B square. It is plus B square for trigonometric function and it is minus B square for hyperbolic function. That's the only difference between them. And when e raised to at comes, shifting happens and the Laplace transform becomes S minus A by S minus A the whole square minus B square. In same way, L of sine h bt will be B by S square minus B square. When shifting happens, as e raised to at comes into picture, it becomes B by S minus A the whole square minus B square. Now we'll have a look at the Laplace transform of the derivatives. Okay, for the real valued function f of t, we know that L of f of t is equal to f of s. Now, L of the derivative, f dash t is the derivative of f of t. So, L of f dash t will be not f of s. It gets changed to s into f of s minus f of 0. F of 0 will be the functional value when t becomes 0. That is when the time variable becomes 0. So, that is a starting point. So, L of f dash t will be s f of s minus f of 0. Now, what is the Laplace transform of the second derivative? So, L of f2 dash t will be s square f of s minus s f of 0 minus f dash 0. So, please notice that all the functional values, f0 will come into picture, f dash 0 will come. So, when we take L of f3 dash t, all these values again will come. Okay, so these are the Laplace transform of the first derivative and second derivative. Now, why are we studying this? We are studying this to solve the ODE problem. So here we have an ODE problem, d square y by dt square plus 4y equal to 0. We can use Laplace transform to solve this ODE equation. The initial conditions are given. The functional value at x t is equal to 0 is 2 and t dash 0 is equal to 0. So now the given equation, we have to take Laplace transform. When you take Laplace transform of y2 dash t, we'll apply the Laplace transform of the derivative formula number 2, which is s square f of s minus s f of 0 minus f dash 0. So here our f variable is y. So we'll take capital Y and small y instead of f of s and f0. So we have s square L y of t minus L y of t is f of s actually, minus s y at 0 minus y dash 0. So L y2 dash t, we applied the second formula plus 4 times L y of t. Okay, so we put the initial condition. Next step, we put the initial condition y at 0 is 2 and y dash 0 will be 0. So that term, middle term is gone. So now we have two terms containing L of y of t, which is our f of s. So we combine the terms s square plus 4 into f of s minus 2s is equal to 0. So our f of s term is, that is L of y of t, is 2s by s square plus 4. Okay. Now we have f of s, but now we have to convert our f of s back to t. We are in the frequency domain. We have to come back to the t domain, time domain, to get the answer of our ODE. That is t variable or x variable we have to find. From y to x we have to come. So we take the inverse Laplace transform of the present function, which is 2s by s square plus 4. So when you take that, you will get 2 cos 2t, because s by s square plus 2 square is a Laplace inverse Laplace transform of cos 2t. So the functional value of the solution to our ODE is 2 cos 2t. Thank you.